Laura. Okay. Okay, so here we'll talk about the convergence of the renormalized model for the generalized KPZ equation while preparation maps. We can start. Okay.
Thank you for the invitation, and I'm glad to talk here in this conference. So today I will present some semi-general convergence theorem. Okay, I can speak louder. Okay. Yeah. Okay. I can speak very loud, so. So what I was saying is that today I will present some semi-general techniques for convergence of models in the context of regularity structures. And the main example that we have in mind is these generalized KPZ equations. So I'm not presenting for the moment a general theorem as the level of the one that Martin Hairer and AJ Sandra presented, but it is an alternative where you have part of it is general, but there are some cases that you need to treat by hand. So this is a joint work with Ismail Bayel and Oussama Nadine, who is a PhD student of mine at University of Edinburgh. So briefly, I just recap on the model. So this is the generalized KPZ equations. So the difference with the KPZ equations that now you have some nonlinearity in front of the quadratic terms, and also you have to treat the multiplicative noise. And so why these equations? Okay, there is an application of a random strings on a stochastic evolution of random strings on manifolds. So this is a geometry context. Here we just look at the flat case, and that's already a challenging equations historically because there are quite a lot of terms to control. But for those who are familiar with QFT, this is a super renormalizable in the sense that we just have a finite number of terms to control. And this equation was motivating a good motivation for introducing general techniques for singular SPDs because you already have 40 terms to control or to take care in the expansions. So the idea of regularity structures introduced by Martin Hairer is to say that, okay, now I want to solve these equations, but I want a local descriptions of my solutions, U. And this local descriptions is governed by some finite sum over indexed by some combinatorial objects, decorated trees. So I present them in the next slides. And these decorated trees are actually an abstract encoding of some stochastic iterative integrals. This shows up when you iterate your PK iterations at the level of the equations. And because there are some nonlinearities here, what often we do is that here in regularity structures, this is a local expansions. So there will be a base point here, X. So if you want, you will consider the stochastic iterative integral, but they've been recentered around the point X. And in a nutshell, the theory tells you that you have a big black box that tells you that you just need to construct or understand these objects, the stochastic iterative integral, and that gives you the solutions. Then you have the correct topology for doing a fixed point for the equations. So in this talk, I will mainly focus on these objects and explain how to construct them or what are the tools for constructing these stochastic iterative integrals. Okay, so then some words about these objects. So first, as I say, maybe forgot to say, is that here at the level of the noise, we think of space-time white noise. So what we do first, we try to regularize a space-time white noise with some here with a convolution with some modifier, so a smooth compactly supported functions. And here it's been rescaled according to with epsilon. And here we use a 2-1 scaling or parabolic scaling in the sense that times counts double in comparison to space. And then here I'm able to define the stochastic iterative integral, but this one has not been recentered. So these are just the objects that you will get by performing some PK iterations. So for instance, here I have the first term, which is this tree. So here the white dot correspond to the space-time regularized white noise. Yeah. Oh, okay. Okay. So if I look at this stochastic iterative integral, I have like two noises. So on the bottom and on the top. So this corresponds to the regularized space-time white noise. And I take a product with here I have the convolution of the heat kernel or some truncation actually of the heat kernel, which is used in the theory. And this product, for instance, this tree is coming from this product. Sorry. Here I have a product, so Xi, and here if I plug the solution of the stochastic linear equation, I got this product, which will be this one. Okay. So then we can think of there are other type of products in our equation that give us other type of trees. So this one where you have the dash edges, correspond to a partial derivative in X on my kernel, space-time convolution with my noise, and it is squared because this corresponds to a product at the level of my trees. And the corresponding term, this term is coming from the fact that you have to expand the X of U squared. Then, of course, these terms, if you want, they are obtained like just after one iterations. But if I want to go further, so I increase the depth of my trees, this will correspond to further iterations of my PK iteration, which is given, for instance, by these trees. So on that tree, for instance, if I'll start with rightmost edges, so this one, which is a plane edge, this corresponds to this convolution of K of space-time convolution with psi. Then I move on, I have this edge, that corresponds to dxk space-time convolution with this noise. And then I have this tree on the leftmost locations. So I start with the convolutions of this kernel with a partial X. And then inside I have this tree that I already encountered, which is this one, that will give me this stochastic, this product. So then, of course, you can iterate this process. And here I've presented trees with two leaves, which are these, yes, without these two. And here I have one tree with four leaves. And in fact, in KPZ equations, by some power counting argument, you know that you just have to restrict yourself to trees with four leaves, which give you already 40 terms, but which is in some sense quite small, okay? So then what happened is that, okay, if I analyze the stochastic integral, so I always terminate by some noises, which are regularized. So then when I compute the covariance function of these noises and I assign epsilon to 0, it will correspond to direct functions. And now I have to understand what is the behavior of this kernel, because this kernel would be singular at the origin. And for instance, for this kernel, because this corresponds to some version of the id kernel, we suppose that you have order 1. So it would be singular order 1 at the origin. So be careful here, the size of the space, because we are working with a parabolic scaling is to 1, so it's 3. So it's 1 here for this kernel. Okay, now, of course, because these objects, when I will remove or send epsilon to 0, there will be distributions. So I have to test them against, to have a test function here. And on my graphical notations, the test function, I mean, this notation has been introduced by Martin Hairer in this works, is that you can use here a green dot. So you have a specific dot, and then you have your test functions. And because this stochastic iterative integral, can be viewed as some polynomial in terms of the noise, actually they are some kind of Gaussian process. And then if you want to control them, you have to control their variance. So what you want to need is that you want to control the variance of that term. And when you compute the variance of that term, actually you move from these trees to Feynman diagrams, in the sense that you will create some pairings. So for instance, here I've represented a tree with 4 noises here. And then when I compute the variance, what happens is that I pair, or I use a weak identity. So I have to pair the noise 2 by 2. And so if, for instance, here I pair these 2, so this gives, okay, here I compute the variance, so I put 2 copies of the trees. So I take this tree and I just put another copy on the side. And what I do then, I pair the noises. So you can see here you have it's a mirror graph. So here I can just cut it and I got the same graph. And the purple dot represents the pairing of the noise. And that's just the covariance of this space-time wide noise, which is given by just a convolution of the modifiers. And if I send the epsilon to 0, this gives me a Dirac, okay? So you can see that you have these purple dots, and that create the mirror graph, or the graph actually you want to control the bounds. Another remark is that we will also want, when we will recentered, this test function will be scaled at the point. And so that will be also important that we don't want only the convergence of this diagram, but you want to have a correct behavior around that point. So that's an extra ingredient that we have to care about. Okay, now I would like to talk about Malyavan derivatives, because we use some spectral gap inequalities. So the idea is that, okay, this is a number of noise, if you want, or white dot in your trees, and you will consider Malyavan derivatives on this stochastic iterative integral. So this means that you will consider this element, this Malyavan derivative, and an element of this space. Okay, technically, I mean, what does it mean? So for instance, I have to take a tree here with 4 dots. And when I compute a Maillard derivative with H, meaning that I replace one of the noise by H. So this actually improved the regularity in the sense that this space-time wide noise is a distribution and H would be actually better behaved than the space-time wide noise. So that's the term that we compute. So here I replace it here, but I could have used another spot. This is a derivative, so I can replace another spot with H. So I can do also 2 derivatives. So then I have a choice of replacing 2 white dots by H1 and H2. So here I've taken a tree with 4 leaves, and here you see you just have 2 white dots. I could do it here and here. So what does that mean at the level of the Feynman diagrams? When I take this Maillard derivative, it's just I take part of my diagram, and now I become more regular. So in the sense, when I have to perform renormalisation afterwards, I don't have to renormalize this part. So if you want, it's a way to increase the regularity of your diagram, and then you have just to focus on the singular part, which will not actually contain this H. So it's just a way to organize the computation a bit differently. So for instance, here, if I look at that diagram, the only term that I have to care about would be actually the pairing between these two, or this sub-diagram that will diverge. You see, if I do the pairing, actually, I think it's not divergent. And here you may have to care about what is happening on the top. So in a sense, it reduces the complexity of the treatment of these terms. And okay, what happened here? So for instance, here I'm taking the expectation of the terms above. So here I have to merge these 2 white dots. I got a purple dot. So then I got this actually it's a divergent subdiagram. Here I have to merge these 2 dots. So I got this Feynman diagrams. And here I merge these 2 dots on the top, and I got this one here. Okay. Yeah. The motivation is that we use then spectral gap inequality. So I will explain on the next slide. It would be comparable to do Wiener co-expansions. Because the Maillard derivatives, when I take it here, I know, for instance, that term is quite easy to control because I know that this part, or the part that will contain H1 or H2, if I look at the subdiagram, this will be not singular. We expect to will have to act elsewhere, not on this. So this reduce the complexity. Then if you have to show the convergence of this term, when you have taken 2 Maillard derivatives, you just have leaves, and you just have to treat subdivergence with 2 leaves. So this is a reduction of complexity. No. I mean, potentially you can try to do that, but here I'm just working at the level of the Feynman diagrams. Okay, so then what we use here, it's an identity which was, I think, first introduced, or used by Linares, Otto, Tempelmayer, and Satsoulis, where they actually did a recursive proof for the construction of multi-indice regularity structures. And the idea is quite simple, is that you look at your model. So here you are in this L2 norm, and then you bound it. This is with some assumptions on your noise. You bound it by an expectation of these terms, plus you have the first Maillard derivative, and then you take this L2 norm. So here, when they were doing they were using the fact that because you put the Maillard derivatives, these terms as part of these diagrams, where you have it's not singular. So then they were using an additive argument based on that. And the idea was that first, for this term, this term was fixed to be 0 or like be finite, by having a choice of renormalisation constants. So these were imposed by you want to kill that term. And here, what we did differently in this work, we say, okay, now we want to iterate this second term. And if we iterate, we get this true type formula where I have this term, which now is bounded by a sum over Maillard derivatives up to the number of noise -1. Plus, I have, if you want, high order terms where I've replaced all the white dots by some H. Okay. So that term, for instance, is quite easy to treat. There is no divergence because all the H are there. And the terms that you need to control are all these expectations where you have to put some H up to the number of noise. So in the case of KPZ equation, it's quite simple. In the sense, it's reasonable because here it is Gaussian, so I need to have at least an odd number, even number of noises. So for instance, if I look at this sum, I can just either have 0 Maillard derivative or 2 Maillard derivative, because then I just have 4 dots, white dots, 2 white dots, and that's it. Then I just reach the main term. So in the sense that here you just have 2 terms to control. Other questions? Yeah.
What's the norm that?
It's a norm on this H, this L2 norm on this H. So you just take the L2 norm with regard to the H here. Yeah. I mean, if you have several Maillard derivatives, there would be several H. There would be H1 up to HK, the number of Maillard derivatives, yes. Okay, and so that's the bound that we obtained with Ismail, that we can bound the leading order terms, where you are replacing all the noises by this H. And okay, here I say this is localized, so that's why we got this bound. And this term, this number, could be seen as the degree of the diagram. So that would be the degree of divergence of the diagram. And here B minus, if you want, this is 40 terms, so you have just a finite number of terms to check for constructing your solutions. And I can get the same bound. So here it's a model without renormalizations. And here I can get also bounds when I put Maillard derivatives, but here I have to choose a model where with a suitable renormalized model. So I cannot take the model without renormalizations. Because here there will be some noises. I haven't replaced all the noises by H, so I will expect to have to care about some subdivergence and to do some renormalizations. Okay, so now I would like to explain the tool that we will use for understanding these Feynman diagrams. So, okay, you know that we have some green edges that represent this test function. And then we have a big diagrams where we are using K, so some version of the kernel, which is singular at the origin. You have also partial of X of K. So this is another kernel, which is a bit more singular because I take a partial derivative in X. And then you have also modifiers, or like this, that will give the right function in the limit. And so now the idea is that, okay, if I consider this diagram, okay, I can try to show the convergence, but I want also the diagram to be small around a certain point. So now what I will add on each of these edges, I will suppose that I'm given Taylor expansions. So on each edge, I will have this kernel. So this will be the kernel here. So these are the 2 variables associated to the extremity of the edge. And now I subtract a Taylor expansion where I have another on my Taylor expansions. And I have a point here in which I perform my Taylor expansions. So the point will be a point variable in the graph. So here, what happened is that you have 2 choices. So imagine this is an external point, for instance, Z, that this is something you want this diagram to be recentered around that. So then you could imagine that the Taylor expansion here will be taken in this point Z, and this will be just a recentering. So you want the diagram to be close, to have a behavior close to that point. If this point is not equal to Z, but to another point in the diagram, you may expect this Taylor expansion to come from renormalizations. So we may expect this Taylor expansion to have an effect when certain variables are closed, and this will produce some gain that will counterbalance subdivergence. And that's why you need an order here. So this order could be the order of divergence of some subdivergence in the diagram, and then you put the right Taylor expansions toward this point, and this gives you the effect that you want. So another remark, so the kernel here, as I say, you have different choices. So here, if I work with this kernel, is singular with degree 1. Here, if I take a partial derivative X, will be degree 2, so I will be more singular. And for my modifiers, because they converge to Dirac, we could assume that they are like behaving like 3, so like the size of the space. And so these kernels, they are all singular toward this point. So this would be the singularity of my kernels. So this is good because then I can do a power counting. We will do a power counting for detecting divergence based on these singularities. Okay, so here I just, so this is a complicated formula. So the idea is that I suppose that I'm giving a graph where someone has put this stellar expansion for me. And now I can just use a pure combinatorial way to check if the diagram converge or if it is recentered around point A. So this what I present here, it's the generalizations of a theorem developed by Martin Hairer and Jeremy Quastel that were assuming that. And it was used for a while in the SPD's communities for saying that if you check certain bounds of this type, then it converge. And okay, we did an extensions because the extension here is that in the original paper, I think they were just considering Z to be small z, and then they were having another notation for renormalisation, so there was not the freedom of taking any point in the graph. So just to comment a little bit on this identity, so I will not have time to define all the terms, but just to give you an idea of what they mean. So for instance, for those who are just interested of the renormalisation of the convergence of the diagram, you can just drop the second one. So the first one will be actually tells you that you have convergence. So then if one thing, okay, this is complicated because your effect of renormalisation to give you some improvement with this rate of divergence. So what you need to focus is that here on this term, if you select a number of edges in your graph, and then you sum over the singularities, which are these A subscript E. And you want them to be smaller than the size of the space, which is 3, times the number of variable of integration minus 1 that you choose. So if you forget these two terms, this just tells you this is just an integrability condition. So that's the minimum that you want to check. And that's the integrability condition that will fail into diagrams, because if you do the power counting, you will see that the singularity is bigger than the integration variable that you have. So you need to do something. And the something, it would be the cure, if you want, would be these terms that provides this, especially that term. That's why I'm saying that I want my point, the point on which I perform the Taylor expansion, to be included in the set I'm taking, just to get the effect of my Taylor expansions, renormalizations. And for this other identity, it goes the other way. So this is because we want the term to be local. So here, I will not expand too much on this, but you have also the effect of the Taylor expansions that need to be taken into account for these terms. Also, part of these identities or variant of these identities were used, I think, in A.J. Sandra and Martin Hairer in their theorem for the general convergence theorem for renormalized model. Okay. So we are given this. Okay. Then you say, okay, I suppose that I have some graph with correct Taylor expansions. Now I need to check that. So there are two difficulties. First, I need to know how to construct this graph from my trees, which is clearly not obvious. And then I need to know how I check these identities, because they are quite, they are taken over all subsets of nodes. So this is quite, so it's a very nice theorem, because it really is telling me just purely on power counting if my diagram has a certain behavior, but could be useless in practice. Okay. So I will explain now. Okay, before I just say that, okay, now I work with my graph here is associated with all these kernels on each edge. So I have all these Taylor expansions. And now, because it's a mirror diagram coming from the variance, I have two test functions at two different points here. And then what you say that if the graph satisfies the assumption that I presented before, you get this bound. So you get a bound with some behavior in lambda, which is coming from the behavior lambda that you put on the test function. And then you have a degree here, alpha, and alpha, it's just the degree of the diagram. So you just have the number, I mean, the size of the space times the number of nodes minus, you subtract all the singularities. So that's just computing the degree of the diagram. So that's the result that you obtain. If you satisfy the bounds, you get this theorem. Okay. Okay, now I will explain briefly some kind of algorithm, how to construct these diagrams and how to use these bounds, how to check these bounds. So first, so we want to construct diagrams out of these terms. So here I've put k Maillard derivatives, replacing k noises by some h. Okay, there will be some renormalization, but the renormalization which shows up when actually we do our manipulation. So I will explain them in a minute. And so we assume that there will be some recentering. So at the beginning, we have Taylor expansion, which are all toward this point Z, this external point. And now we can say, at least this is the basis, the start, that when we produce this diagram with all this Taylor expansion around the point Z, at least we get the second bound. So the recentering is satisfied. Okay, so that's an assumption that we start with, and this is just because this model, has been constructed recursively, and one has put this recentering correctly in the diagram. So we assume that 2 is satisfied, that the recentering is satisfied. But as I say, if we don't put the correct, but the renormalization hasn't put yet. So in the sense that the first condition of summability could be not satisfied. So then the idea of the algorithm is the following. Instead of starting from a diagram and then check all the conditions, I start from a diagram that I know some condition has been satisfied. And now I will try to evolve step by step. So if I put some renormalization, I have to check that the second condition is still satisfied. And I remove one problem in my first condition or summability conditions. So progressing step by step, then converge gradually to a graph that will satisfy all the conditions. So that's the strategy that we want to use. As I say, so the recentering is okay, but convergence may fail. So then you can detect them because these are these sub-diagrams or sub-tree of negative degree. I mean, you have a power counting for detecting them. And then you need to perform some local transformation, which actually is renormalization by putting the correct Taylor expansions for getting the convergence. And then by doing so, you will make appear some renormalization constant, and these are the ones that you will have to subtract. Okay. So it looks still a bit tedious because you have to do it by hand, but I mean, for general KPZ, there are just 3 with 4 leaves. So divergence with 2 leaves are easy, you can easily characterize them. If you want to generalize the perspective, you will need to work a bit more, like niceties of divergences and overlapping or not. So this could be, I don't know, maybe we are trying to see if you can generalize this, but this would be for what I presented here, it's just for one subdivergence. Okay, so now I start with a diagram. So here I suppose that I have a graph G, so something a bit bigger upstairs, and now I'm focusing on these diagrams. So here, by just power counting, I've just identified that I have these sub-diagrams that correspond to this integral. So here, okay, it's a prime, but it corresponds to the partial derivative in X, and then I have my purple dot, which is convolutions. So I have these diagrams. So now I do the power counting. So this dash dot here, they correspond to this partial derivative on K, and we know that this is 2 in the definition. So I just, it was here, so this is 2. Then I have 2 of them. So I have like 2 plus 2. I have this purple dot. So this corresponds to something that will converge to a Dirac. So I have a plus 3. And now I have like 3 variables. So I have like 3, but it's like 3 minus 1, so it's 2. So, and the size of the space is 3. So I have 3 plus 3. And now we can see clearly that the power counting of the first condition is not satisfied, that this is something which is divergence of order 1. Okay. And so now what we do, I do an exact identity. I say, okay, I have identify some subdivergence with my power counting. So I will try to move the edge or from the entering edge here toward the root. So here, the root, you have the point Y, so I will put it here. So this is just exact, okay? So here I'm not doing any approximation, I'm just producing an exact identity. So what happened here is that I put a Taylor expansion here up to order 2, just to cure this subdivergence. And this is done, this is this Taylor expansion, okay, toward this point Y. And then, okay, because I've added these Taylor expansions, I need to put the counter terms here, just to have an exact identity. And this Taylor expansion here gives me the correct behavior to counterbalance this subdivergence. So then I can say that this graph satisfies condition 1, at least for this term, condition 1. And then you say, okay, I may have other graph here. They, of course, don't satisfy condition 1, but you see that you have detached this edge. So now you have this term. And so if the term is translation invariance, then it's just a constant, and that's just something that you need to remove. So you just make appear the the constant that need to be subtracted. Yes, and then, okay, you have another constant here because you go to higher order, you introduce some x. So here I've put some yellow loop here where I have some x1 minus x. So this term, for instance, would be of degree 0. The previous one was degree 1. Okay. So this is just a way to, I mean, this is very simple. Just have one subdivergence and one incoming edges. Are there any questions so far? Good. Okay. Now what happened is that, well, here I was assuming that on this edge there were no Taylor expansions. But you may assume that there was already a Taylor expansion. And the most, here in the case of general KPZ, what we expect is that a Taylor expansion for the recentering. So what happened is that you can do the same trick, I mean the same decompositions, and then you move out, you transport this recentering. So this gives me, for instance, if I have a recentering here, I have here the correct renormalization, so this is the same term as before. But for instance, that term will need a recentering, which is coming actually from here. So you just group the recentering on put it on the correct term. And this is also work in the telescopic sum. So this is this first Taylor expansion, it is here. The one for the recentering, which is this term, it is put on the second term, which is here. And the third term, you don't need any recentering. So this, and then the challenge is to say, well, if I do these manipulations, I want all the terms also to satisfy condition 2, because I've moved some Taylor expansion for the recentering, and so I have to check that this condition 2 is satisfied. But it's not so complicated because it's just one step. So it's just locally one part of the diagram that you need to check this condition 2. So let's explain how you can move this Taylor expansion. Okay, now more complicated diagrams. So here I just, so this, I think it's a diagram which is not covered by Hairer and Quastel, is that you put two incoming edges, but not on the same spot. So they are on two different spots on my previous divergence. And here, basically, you have like two problems. Because then you have this this purple line that could be interpreted as a subdivergence. And then you have the main divergence, which is of order 1, which is this term. So here you have a bit of degree of freedom by moving this edge and doing this telescopic sum. So here what I try first to cure this white dot, this purple dot. So for instance, I put a Taylor expansion and I move this edge toward this one, creating these subdivergences. And so now I'm in the configuration, so that term will be fine because I put the correct Taylor expansions that actually cure the divergence and also the subdivergence. But these two terms, of course, you need to continue. In the sense now I'm just reducing to the case where I just have two incoming edges on the same spot. Okay, so I have to treat this these two terms here separately. And then, for instance, here I put my Taylor expansion on this one, I move this edge on this one, so it gives me these two terms. And now I proceed for the second one, and I would get my renormalization constant. Okay. So that means that I can work with a subdivergence with incoming edges on different spots, and I can just one by one move them, and I produce a lot of graphs which are actually having the correct Taylor expansions, and that will satisfy the, okay, the pointer is not working. Okay, that will prove the correct Taylor expansion that will satisfy allows me to check to see that the condition 1 is satisfied. Okay, so what happened here is that I start with a diagram, I do my manipulations, so I produce a lot of diagrams that satisfy condition 1 and 2, and in the end, I got something which is like a counter term with a constant. So then, of course, this term, I cannot reduce it anymore. I mean, I have to remove it. And this is what dictates, or if you want to say that you need to, this term, you need to remove them with renormalizations. So then what you can do, you can take you can start with a model which has been already renormalized and will contain this term, will subtract this term from the beginning. And we're asked to say that actually you subtract this term in the end. Okay, now I would like to explain a bit how the renormalization is done on the model, because so here it's what I call preparation map, or maybe local renormalization map, depend. I don't know what is the best terminology for it. So the idea is a bit the way we did it. we focus on one point, and then here in the graph, and then here you do the local renormalization. So you look at all the subdivergences attached to a point. And then what happens is that you do it recursively. So you start with your tree structure, and you have a mapping between subdivergent trees and subdivergent diagrams, because the trees from the trees you construct the diagrams. So negative subtrees give you negative subdiagrams. And so you start recursively on the trees. And what's happened is that, okay, you have a multiplicative map here, but before being multiplicative, you need to cure the divergence with some map R at the level of the trees. And then when you cure the divergence, you can put this Taylor expansion. So this would be the recentering. So these are the Taylor expansion that you put on your graph for the recentering, and they are done in this definition of the model. One technical point is that this renormalization, as I say, should be compatible with Malyavan derivative, because Malyavan derivative introduce objects which are more regular than the noise. So we ask, for instance, this renormalization map to commute with the Malyavan derivatives, because we expect that renormalizations will not touch the part where you put this H1 up to Hn. And then it gives you also this nice identity, is that you can show that if you take K-Malyavan derivatives on your renormalized model, this is the same as taking your renormalized model where you put this abstract Malyavan derivatives. So it means that at the level of the tree, you already put different noises. I mean, you replace this white dot with this H1, and this is encoded directly on the diagram. So by doing so, and you can identify that the subtraction process is correspond actually to this R, that is actually removing a subdivergence at a point when you do it recursively in your tree. So this allows you to identify that actually these terms, you already have them, and then they just kill the subdivergence which are produced by these local transformations. Okay, just to like to give some perspectives. So as I say, what I presented is specific. I mean, finite number of terms, tree with 4 leaves. Most of the time, you just have to treat one subdivergence, because this is just a subdivergence with 2 leaves, produce small diagrams. But it already contains some features, in the sense, I know how to treat by hand exactly by doing this subtraction principle or introducing these Taylor expansions, how to treat a subdivergence with incoming edges not on the same spot, but on different spots. So I have some kind of algorithms that allow me to treat these terms. And I have also a very nice theorem that tell me that I'm able to say that if I have put the correct Taylor expansion everywhere, that I get the correct bond on the diagrams. So then it's just, the difficulty is just to try to iterate this procedure, or this local transformation by moving the edge, which are kind of exact. And also, I would like to say it's more toward maybe SPD community, but this work also in the discrete setting, where you discretize time and space. So for instance, I did a work with Oussama Nadine based on some discretization given by Martin Hairer and Dirk Gerhard on the stochastic multiplicative equations. And so then we want to go toward the general convergence theorem, potentially, or this, I cannot pronounce, say too loud, but could be potentially maybe some application to Malyavan calculus, because we are manipulating these diagrams when you have this H and we're deriving bounds on this. And this is maybe toward more the community of QFT, which is in the room. If there are like similar problems where similar ideas of doing this local transformation one by one, as I presented in this talk, that has been appeared in the context of QFT. So, because what I presented is really something exact, and then I produce some big object graph with some decorations, and I just have to satisfy these weights, and if I put the correct Taylor expansion, it works. So that's a question to, a general question, I would say. So thank you for your attention. Maybe a bit too short, but